Alright, let's talk about one of the greatest adventures in human history. It's a story of ambition, of curiosity, and of sending a piece of ourselves out into the great cosmic ocean. We're talking about the Voyager missions. Think about it. In the late 1970s, we built these two incredible machines, Voyager 1 and Voyager 2, and we flung them into space. Their mission was something straight out of science fiction, to take advantage of a rare planetary alignment that happens only once every 176 years. This grand tour would let them use the gravity of one giant planet to slingshot to the next, a cosmic game of pinball that would take them past Jupiter, Saturn, Uranus, and Neptune. The real star of this particular story, though, is Voyager 2. While its twin, Voyager 1, took a different path after Saturn, Voyager 2 was tasked with continuing the journey into the unknown. It was headed for the true frontiers of the solar system, to planets we had only ever seen as faint fuzzy dots through our best telescopes on Earth. The journey of Voyager 2 was not a simple straight line. It was a carefully choreographed dance across the solar system, a testament to our understanding of orbital mechanics and gravity. After launching in August 1977, its first major stop was Jupiter in 1979, where it discovered volcanic activity on Io and used Jupiter's gravity as a cosmic slingshot. The path to Uranus was long, cold, and dark. For more than 4 years the spacecraft sailed through the vast emptiness between Saturn and Uranus, a journey of over 1 billion miles. During this time, the team back at NASA's Jet Propulsion Laboratory had to be patient. The light travel time was immense. A signal sent from Earth would take hours to reach the probe. As Voyager 2 got closer to Uranus, the anticipation at NASA was palpable. This was our first ever up-close look at an ice giant, a completely different class of planet made of heavier ices like water, methane, and ammonia. The engineers had to prepare the spacecraft for an environment it wasn't entirely designed for. The sunlight at Uranus is about 400 times weaker than at Earth, requiring incredibly precise programming for image motion compensation. Before Voyager 2's historic arrival, Uranus was a planet defined more by what we didn't know than what we did. From our vantage point on Earth, it appeared as a small, featureless aquamarine disk. We knew it had a handful of moons, 5 to be exact, Miranda, Ariel, Umbriel, Titania, and Oberon. But these were just faint points of light orbiting the planet. The biggest mystery was its extreme axial tilt. While Earth is tilted by a comfortable 23.5 degrees, Uranus is knocked over completely on its side, tilted by a whopping 98 degrees. This means it essentially rolls around the sun on its side like a barrel. For a quarter of its long 84-year orbit, one pole faces the sun directly, while the other is plunged into decades-long darkness. Scientists had a wish list of questions they desperately wanted answered. At the top was the planet's magnetic field. Did it even have one? And if it did, what would it look like given the planet's crazy tilt? Another puzzle was the presence of rings. In 1977, astronomers discovered Uranus had thin, dark rings. Nothing like Saturn's bright rings, but rings nonetheless. From Earth, they were practically invisible. January 24, 1986. That was the day. After a journey of 9 years and nearly 2 billion miles, Voyager 2 made its closest approach to Uranus. The tension at JPL was electric. The spacecraft was hurtling towards the planet at immense speed, and the entire encounter would be over in the blink of a cosmic eye. The radio signals from Voyager 2, traveling at the speed of light, took 2 hours and 45 minutes to reach Earth. They were essentially watching a ghost. By the time signals arrived, the encounter was long over. As the first data streams began to populate the screens at Mission Control, a mixture of relief and astonishment filled the room. It worked. The spacecraft was alive and talking. The initial images that came back were stunning. The featureless blue ball we knew from Earth was revealed to have subtle cloud features, including faint smudges indicating atmospheric activity. But it was the data from the magnetometers, plasma wave sensors, and radio science experiments that would truly turn our understanding upside down. This fleeting glimpse into the abyss was about to change everything. The first major shockwave to hit the scientific community came from the magnetometer data. Uranus did have a magnetic field, but it was unlike anything we had ever seen. Voyager 2 discovered that the Uranian magnetic field was tilted by a staggering 59 degrees from its rotational axis. Imagine if Earth's magnetic North Pole was in Florida. That's the kind of absurdity we're talking about. The magnetic field wasn't just tilted, it was also significantly offset from the planet's center. As Uranus rotates, this wobbly magnetic field corkscrews through space, creating a magnetosphere that undergoes wild changes with every rotation. The discovery was so bizarre that some scientists initially thought the instrument might be malfunctioning, but the data was clear and unambiguous. Uranus was a magnetic monster, a true freak of the solar system. Then came the images of the rings. We expected maybe 9 thin dark bands. Voyager 2 revealed a much more complex system. 11 rings made of material darker than coal, some of the blackest stuff in the solar system. The images revealed that some rings were strangely clumpy and uneven, held in place by tiny shepherd moons we didn't even know existed. They were ghost rings, absorbing almost all the light that hit them. Perhaps the most visually stunning revelations came from the moons. Voyager 2 flew closest to Miranda, and the images were jaw-dropping. Scientists expected a simple cratered ball of ice. Instead, they saw one of the most geologically bizarre objects in the solar system. Miranda's surface was a chaotic jumble with giant canyons up to 12 miles deep and Verona Rupes, thought to be the tallest cliff in the solar system. The flood of data from Voyager 2 didn't just add new facts to our knowledge of Uranus, it forced a complete rewrite of the textbooks. Before the flyby, Uranus was the boring giant. These discoveries shattered that perception forever. The mood at JPL was one of exhilaration mixed with bewilderment. They had sent a probe to investigate a planet and ended up discovering an entirely new kind of planetary system. The tilted magnetic field challenged our fundamental understanding of planetary physics. The leading theory now is that Uranus's dynamo isn't deep in its core, but in a slushy, salty ocean of water, methane and ammonia surrounding a smaller rocky core. Scientists realized these worlds might be a distinct class of magnetospheres, fundamentally different from both terrestrial planets and gas giants. Uranus became the prototype for a whole new planetary model. This is why the scientific community is clamoring for a return to Uranus. A dedicated Uranus orbiter and probe mission is at the top of the planetary science wish list, capable of watching seasons change and mapping the magnetic field in 3 dimensions. The allure of Uranus is stronger than ever because it represents a class of planet incredibly common throughout the galaxy. By understanding Uranus, we're learning about the most common type of planet in the universe. Voyager 2 gave us the first tantalizing chapter of an epic story, leaving us with more questions than answers. The pale blue dot is calling us back, holding cosmic secrets that extend far beyond our solar system. The legacy of Voyager 2 is a legacy of humility and wonder. A reminder that the universe is always more creative than we are, and that our greatest discoveries often come from our most shocking surprises.